Hello, everybody. So what we're going to be looking at today is section 3.1, which is algorithms. So this is actually the second lecture on this topic. We started it in the previous lecture. I had some typed up notes that we used then, but the rest of it's not typed up, so I will just write it as we go. So let's go ahead and mention what you're supposed to know already. So you need to know what an algorithm is, first of all. So what is an algorithm? An algorithm is just, I'm going to summarize here, not write out the whole thing, but a set of instructions for solving a problem. A set of instructions to solve a problem. Okay, so if you want a better definition, then check the previous lecture where I type out a longer, more complete version of that. Okay, what else are you supposed to know? So we also coded up, I believe, a couple of simple algorithms. Actually, did we? Yeah, we did, right? Yeah, we did two algorithms in the previous section. So we looked at last lecture. We also covered what? Two simple algorithms. One is so simple you might not have even thought of it as an algorithm. So what are they? We had one of them was finding the maximum of a list of numbers, finding max of a list of numbers. And the other one that we did was linear search. Linear search to find a certain value. Actually, I'll say to find the location of a certain value. Find the location, which we described as an index of a number in a list. All right, so that's what we did in the previous lecture. So if you're looking for that, then go find part one because this is part two. Okay, so let's just get into it then. So the idea is this. So the rest of this section is covering specific algorithms for searching and for sorting. So so the rest of the section covers, and I think we mentioned this, but we can say it again. What does it cover? Searching and sorting. Right? So what are these? Well, searching, of course, is going to be you have a list. You have a list. Like what's in your list could be numbers, could be letters, could be anything. It doesn't matter. I'll just write numbers. So like 2, 5, 3, 12, 15. Why do I have one comma? I don't know. Right? So you have a list like that. And then the question is, see, is there a 12? If so, what is its index? Okay. And so answering that kind of question, you have to search through the list to look for the 12. And we had some algorithms that did it. Well, not some, we had one, right? So we had, possible algorithms for solving that problem, or linear search, which is the slowest. And then we're going to talk about binary search at some point. What else is there? that might be it in this section, but there are others. And the other topic that we're going to cover in this section is sorting. And so this is where you have a list. Like, I'll make a different list. So like if I go like 2, 15, 4, 1, 3, right? So if I have a list like that and we want to put it in ascending or descending order, I think we're just going to do ascending, but it's really easy to do it the other way. You need to put the list into order. And I'm just going to say order, not ascending or descending. It's whatever you want to try to do. But, what would the output be? Well, it would be this list, but in order. So like 1, 2, 3. I see a 1, a 2, a 3, a 4, and a 15. Right? So that's what that same list would be if I put it in order. 1, 2, 3, 4, 15. And that's sorting. So what are the possible algorithms? Well, there are a lot of sorting algorithms out there, okay? In this section, we don't cover very many. So what are we going to have? We're going to have bubble sort is one that we're going to cover. Another one called insertion sort is one we're going to cover. And that's probably it for this section, but there are others like quick sort and so on. Okay, but we're going to cover the first two and not quick sort. I wrote quick sort. Why? Okay, quick sort. All right, so that's kind of what we're going to be doing then. So let's go ahead and get started. So we're going to start with the binary search algorithm. So binary search. And so first what I'm going to do is I'm going to show you binary search worked out. And then after I do that, then I'll show you the algorithm. So let's see what binary search does. So I'm going to follow the same exact example in the book. You're going to want to look at this because if you have book homework for the section, you'll have to do this by hand as well. So let's just say something about it before I do the example though. So binary search. So what is a binary search? So for binary search, you have a sorted list. So you can't actually do a binary search unless your list is already sorted. So you start with an already sorted list. And you'll see why that's important once we do it. Okay. And then basically what we're going to be doing to do the binary search is you split the list into two down the middle. So you split the list in half into two halves actually. And then what you're going to be able to do, and you'll see how, is that if you split the list into two halves, you're going to be able to tell whether or not the thing that you're looking for is in the first list or the second list, because we got two halves now. Is it first half or is it the second half? So you determine, which you can have a simple test for this, you determine whether the number you're searching for, which we'll call the key, whether the key is in the first half or the second half, first or second half. And then after you do that, well, you've already, ruled out half of the list. So now what you do is the part of the list that you still have left, you're going to split that list in half and so on until you're down to just one single element. So you determine whether the key is in the first or second half, and then split that in half. You split that in half again. You determine whether the key is in the first half or the second half. And then you just keep doing this process until you're down to one single element. Keep going until you find it, or until you're out of entries, because you might be looking for something that's not in the list. So you keep going until you find the key. Or figure out that the number's not in the list. Now, something I want you to notice is I just tried to describe the process in English as well as I could, and I still wasn't that clear about how to do certain things. And that's why, like we were talking about in the previous lecture, that English isn't a great way to describe algorithms necessarily, because a lot of the things that you write in English is not precise enough for a computer to do. Like when I say you split the list into two halves, well, how? How do you split the list into two halves? You determine whether the key is in the first or second half. How? I didn't say. And so on. And I say keep going until you find the key or figure out the key is not in the list. Well, how do you know? So, like what I just wrote here does not actually describe the algorithm well enough to actually perform the algorithm. But I wanted you to have an idea of what it was doing before we actually show it with an example. So let's look at an example now of binary search. Binary search example. We're going to look for, because you need something to look for because we're searching, but we're going to look for 19 in the list. And what list? Okay, so it's kind of a long list. 1, 2, 3, 5, 6, 7, 8, 10, 12, 13, 15, 16, 18, 19, 20, 22. All right, so we're going to look for a 19 in here. Okay, so now if you were going to do the linear search, which we talked about in the previous section, like the way we would do linear search is you would just do this. You would just say, is that a 19? No. 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 And you would just keep going all the way down to here, and then you'd find the 19. But it would take you a lot of steps, right? How many steps would that take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It would take 14 steps to find the 19, right? So that's not efficient. So I'm just going to note this. It would take 14 steps to find the 19 with linear search. And that's why linear search is not good. Okay, so that's just a note, has nothing to do with the binary search. Also, notice that this list that I put here is in order. That's important. Okay, so here's the way you would perform the binary search now. So the way you would do this is as follows. So you need to divide the list into two. You don't have to write what I'm writing in blue. The only thing you would need to write if you were doing this like as a book problem is what I'm writing in purple. So you would divide the list into two in halves. Okay, So what does that mean? Well, how many things are in my list here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 things total. So if I'm dividing it into halves, I should have 8 and 8. So you divide the list into halves and you put the first 8 in one half and the other 8 in the other. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to put, your book doesn't do this, but I'm going to put brackets around these just to make it clear what's in what. Okay, so there's your first 8 elements. So the other 8 elements must be in the other half. 12, 13, 15, 16, 18, 19, 20, 22. Okay, so there you go. So what you do then is you're going to compare the 19 to this number. Okay, the last number in the first list. So you compare 19 to last number in the first list, first half. Okay, so since 19 is bigger than that, is larger, what does that mean? Well, remember that this list is sorted already. So since 19 is actually bigger than 10, then that means that 19 could not be in this half. Just by comparing the 19 to the 10, we know 19 can't be over here. So that would mean 19 has to be in the second half if it's in one of the halves at all, which it doesn't have to be. But if it is, it's in the second half. So since 19 is larger than 10, we're just going to throw out the first half. Okay, but after you throw out the first half, so we just cross that out, then we got the second half. And what we're going to do with the second half is exactly what we did before. We're going to split it in two. So we're going to split second half into 2. So split second into halves. So how many things are in here? We got 1, 2, 3, 4, 5, 6, 7, 8. 8. So if we split it in half, it's going to be 4 and 4. Remember what I said, you only need to write the purple. So go 4 and 4 here. 1, 2, 3, 4. And then 1, 2, 3, 4. Okay. And then we're going to do exactly the same thing that we did before. You're going to compare the 19 to the last element in the first list. So compare 19. 19 is larger than 16. So throw out the first half. Just throw that out. What are we going to do with the rest? We're going to cut that half in half. So split the remaining half into half. What are we going to get? We're going to get 18, 19, 20, 22, like that. Then you're going to compare the 19 to the 19. Now, here's the thing you're probably not going to do. You probably aren't going to notice, like in the way the algorithm is described, you're probably not going to do anything special right here if the 19 matches the 19. We're probably going to keep just doing what we're doing here. We won't even notice that the 19 matches at this point. What you're going to do is you're going to compare the 19 to the 19. So you compare 19 to 19. 19 is not larger, right? So that's different than before, not larger. Like I said, we're not going to notice if it's the same or not, just going to notice it's not larger. If it's not larger, then that means it's going to be in the first half, right? In the previous two, we threw out the entire first half and we threw out the entire first half. Well, we're not going to throw out the entire first half this time because 19 is not larger. We're going to throw out the second half. Throw that out. Okay. So then what do you do after you throw that out? Well, then what you do is you split the remaining halves into half again. So you split the 18 and 19 into 18 and 19. And so at this point, this is where you actually, well, almost to where you do the comparison. So we still keep going. You compare 19 to 18. 19 is larger. So throw out the first half. And you've only got one element left, right? So there's no halves now. You've only got 19. So at this point, once you've got a single element, that one single element, either it's the number you're looking for or the number you're looking for isn't in here at all. Okay. So you're guaranteed that that's the way it goes. So either 19 is your answer or is the key. And it is. Or if you compare the 19 to the 19 and it's not equal, actually, let me rewrite this. If you compare the 19 to the 19 now, so you check if the key, which is 19, is equal to the last number. Which is also 19. But, it doesn't have to be. So your two choices is if it is equal, so 19 equals 19, then what happened is you found the thing you were looking for. Right, so the search was successful. If they were not equal, then you failed and the 19 was not in here at all. Then the key was not in the list. And so your search failed. Okay, so this one did not fail because we found the 19. Okay, now something that we didn't talk about in this example here is we didn't talk about keeping track of an index. Like I found the 19 here, but I didn't actually find out that the 19 was in whatever spot it was, which was what? Was it 14th spot? I didn't find out that it was in the 14th spot. And so when I show you the algorithm, you're going to see that the actual algorithm keeps track of what the index is. And so in the actual algorithm, we would know that 19 was at spot 14, for example. Okay, so that's how you write it. And what you need to write is really just what I have in purple. You don't need to, do all the text that I wrote there. I'm just explaining the algorithm. And that is called the binary search algorithm. So let's look at it. Let's see if I can figure out how to do this. You can't see what I'm seeing, but Something terrible happened. Hold on. It doesn't even make sense. What are you doing? All right. Doesn't even make sense. How do I do this? Okay, there we figured it out. Okay. So I've got the binary search algorithm here. Let me make it big. Okay, so there it is. So this algorithm, you're going to see how it works, but I'm not going to describe it too much here because it is part of your next homework assignment. You're going to be coding this up yourself, I believe. But just kind of the idea here is the way it works is you're always keeping track of a left endpoint of an interval and the right endpoint of an interval. And what that is it's always like when you get it down to here, for example, this is where the L is. Well, is that what they call it? I and J, actually. So that's called I. So I would be like that one right there at that point. And the J is the right endpoint. So that's the furthest to the right that we're looking at, which is there at this one spot. And then what you're going to be doing is you're going to be calculating the midpoint, and the midpoint's halfway. And so this is like the halfway point. So like when you're on this spot right here, um, so what you're going to be doing is you're going to be calculating basically where that 19 is, I believe. Let's see. Yes, that's correct. So you're going to be calculating like an M, and then that's right there. So if you knew where I, M, and J was, then you would know that the 18 and 19 was your first list, and then the 20 and the 22 was your second list, right? Just from knowing like the index 14 or whatever it is. Like yeah, the index 14 and the index 15 and the index uh, 16. Wait, is that right? 14, 13. I guess that's wrong. 13, 14, and 16. Whatever. Point is that like for a particular line of work, like where the star is, you need to know what the two lists are and what the indices are that tell you what they are. So you need to know the I, the J, and the M index. And then you'll know where you are in the original list. And that's how it keeps track of the indices. So it just repeatedly goes through and it's going to be calculating midpoints. And then this part right here is where you throw out one of the halves. And then you repeat that and you repeat that until you're down to one element. And then you get down to one element. You check if it was what you were looking for. So like when it says right there, if x equals ai, then location equals I. So what it's doing is that last check right here, where you've got it down to one element and you're saying, is that the element we were looking for? If so, whatever the current index is the location of, in this case, the 19. If it was not what we were looking for, then you would need to say that we did not find the 19, and that's the else location equals 0. You say 0 if you didn't find it. Okay. Now, none of that is particularly, um, tricky. You're going to be coding this up as one of the assignments that you have to do. This is not hard to code up. The only thing that's hard to code up is, sorry, I have to close Notability here and open it back up. Okay. All right, nice and smooth again. So this isn't particularly hard to code up. The main thing that makes it hard to code up is, this right here. No matter how many times I say it, somebody will mess it up. But this symbol here has a specific meaning. So, there are math formulas here in math. So this is called the ceiling function, and it means round up. Round up to the next integer. And this one, which is what we actually have, means round down. Okay, and it's called the floor function. Also, I didn't write ceiling properly. Okay, so ceiling function and the floor function. Okay, there they are. So how do they work? Well, here's how they work. So examples. So like if you do 3.3, ceiling, you would round that up. So it rounds up to 4. Whereas if you did the floor of 3.3, that means round down. So it's not round to the nearest integer, it's round up or round down. So we're telling you to round up or down. And if you get a number, so like if I do like 3.9, right? That's really close to 4. Ceiling 3.9 is 4. Floor of 3.9, floor of 3.9 is 3 still, right? It doesn't matter how close it is to 4. You're rounding up with the ceiling function and you're rounding down with the floor function, no matter what. If you have an actual integer, so like if I do like ceiling of 7, round up, well, you round up to the nearest integer. So ceiling of 7 is still 7, and floor of 7 is still 7. Okay, so that's how the floor function and the ceiling function work. Ceiling is round up, floor is round down. And that is what is used right here. So this is a floor function. Now, why do you need it? Because what you're doing is you're calculating the index of the halfway point. But what happens is, suppose you have a list with 15 elements, right? If you have a list with 15 elements, then in the binary search, right, you have to divide it. You're going to split. You split it in half. Have to split it in half. But how do you split 15 elements into 2? Right? You can't do 8 and 8 because you don't have 16. So you have to do 8 and 7. Right? They can't be perfectly even because of the odd number. So you have to do 8 and 7 elements. So how do you do that? Well, that's what this floor function does here, because what you're going to be doing is you calculate the midpoint this way, like in the code. It does the floor function, and it's I plus j over 2. So that would be 1 plus 15 over 2. Is that true? Hold on. Is that true? I mean, that would be 8, right? So it'd be 1 through 8. Yeah, okay, fine. I got that wrong. Let me change this. Guess we're going to do 14. Which would be 7 and 7, which is the way. This is annoying. So when you did this, you'd be adding 1 and 14, which is 15 over 2, round down. So you would end up with the floor of 15 over 2, which is 7.5 floor, which would be 7. And so since you calculate a 7, and then that would be your first list is 1 through 7, and your second list is going to be 8 through 14. So 1 through 7 and 8 through 15, 8 through 14 actually, are your lists. And you have to round, right? This calculation has to round up or down because you can't there's no 7.5 element of a list, right? There's only element 1, element 2, element 3, element 4. So there's no 7.5 element. So you have to round up or you have to round down, and it doesn't really matter what you do. But our pseudocode says floor, so we do the floor. And by the way, since we're talking about it, I'll just mention it. I'll mention it more. But in MATLAB, this floor function is, I'll write it, right, MATLAB. You actually write the word floor of whatever you want the floor of. And the ceiling of X, you'll never guess. Ceiling. Well, just seal X. So that's how you implement those. So when you get to this floor function right here, the way you're actually going to implement it is this line is going to say this in MATLAB. M equals floor, open, and then you got to open more parentheses and do I plus j, close, over 2, and then close, semicolon. So that's actually how that line will look in MATLAB. You have to type floor for the floor function. If you leave it out, your code's not going to work. Okay. Okay. So anyway, that is the binary search. We saw one example and we talked a little bit about the pseudocode. We're going to talk about it more because we'll have a lecture on the homework. So that's it for now. That's an intro to the binary search algorithm. Okay. Now, something that we talked about was that in order to use the binary search algorithm, you actually had to start with a sorted list, right? Your list needs to be in order. So to even use binary search, your list needed to be in order. So like you could not look for a number in this list, 3, 14, 2, 5, because if you cut that list in half, how would you know whether it was in the first half or the second half, right? There's not any pattern to things. Can't have it like that. But you could search through 2, 3, 5, 14, right? Because then you would be able to know whether you were in the first half or the second half based on just one comparison. So, so to use binary search, your list needs to be sorted. How do we sort a list? How do we sort lists? Okay, and basically we're going to talk about two different algorithms for sorting lists. So we're going to talk about the bubble sort, and we're going to be talking about the insertion sort. Okay, um, let's do that. So let's talk about bubble sort. Okay, so all right, kind of hard to describe, um, but I will show you by performing it, and then you'll see. So let's do an example first, actually. So example, use bubble sort to put 3, 2, 4, 1, 5 into increasing order. Okay, so let's talk about notation here. So in order to write this, we want to write this in like an easy to understand way. So we're going to be comparing elements in this list to other elements. So um, if I write one of these guys, so like if I just drew like a line like that, that would indicate compare. We made a comparison, but we did not switch the order. But no switch, because we're going to switch the order of some elements. Now, if you see this with arrows on the end, that would mean that we made a comparison and we're going to switch the order of the elements. So we made a comparison and we're going to switch the order. Okay. And also, if I put a box around a number, so like if I have, I'm going to make up different numbers. So like if I had like 9, 33, 45, I don't like those numbers, sorry. If I have like 9, 45, 20, 30, like that, and I put a box around the bottom two numbers, then the box would indicate that these were in order and we're done with them. So box indicates this part of the list is in order and we're already done with. Part of the list is sorted. Okay. So let me show you how bubble sort works then. So we're going to sort our list. So first we're going to do what we call the first path of bubble sort. Okay, so the first pass of bubble sort, we're going to take these numbers in the order that they're given to us, and we're going to write them vertically. I don't know why, they just do. I think it'll take up less space to write, I think. So our numbers were 3, 2, 4, 1, 5. Okay, and so here's what you do in your first pass. What you're going to do is you're going to compare these two at a time. And you're going to compare them starting with these two. Okay? And I put the arrows on there, right? What do the arrows mean? The arrows mean I'm going to switch the order. Why am I going to switch the order? What you're going to do is when we make a comparison like this, we're going to switch the order if they're out of order. And so we're trying to put this in increasing order. And the 3 and the 2 are not in order, right? 3 should come after 2. So these are not in order. So we're going to switch if out of order. And remember, we're trying to put it in increasing order. So bigger numbers go at the bottom. Okay, so we're going to switch. So you compare those. So we compare those, they're out of order, so we switch them. So the next line, we've switched the 2 and the 3. So it'll be 2, 3, 4, 1, 5, right? Because we switched the 2 and the 3. Now, what are we going to compare now? Well, now what we're going to compare are the second 2. So we're moving, instead of the first and second element, we're going to be doing the second and the third, these 2. Should we switch them? No, we don't switch them because these are in order. Okay. No switch because they're already in order. So we didn't do anything here. So I'm just going to write the list in the same order again. So 2, 3, 4, 1, 5. Now, which 2 are we going to compare? We're going to compare the next 2. So we had first and second, second and third. Now we're comparing the third and the fourth. So we're comparing these 2. Should we switch them? Yes, we should switch them, right? 4 and 1 are out of order. 1 should come before 4. So those should be switched because they're out of order. So rewrite it, make the switch. So we have 2, we're leaving it alone. 3, we're leaving it alone. We're switching the 1 and the 4, so 1 and 4. And then we have a 5. And our last thing we're going to do is we're going to compare the last 2 on the list here, 4 and 5. Do we switch them? No, right? We don't switch them because the 4 and the 5 are in order. So hopefully you see what to compare, right? It's first and second, second and third, third and fourth, fourth and fifth. Okay, that's where the comparisons are. If they're out of order, you switch them. I'm going to write this over here. First and second, second and third, etc. You switch them when they're out of order. Okay, so when you get to the end of the list, like we just did, then that's the end of the pass. So we're done with the first pass now, so we start on our second pass. So our second pass, we're just going to start it exactly the way we left off. So it's going to be 2, 3, 1, 4, 5. But here's the thing. At this point, you've looked at every single element in the list, and we always moved the one that was bigger to the end. So like from here to here to here to here, after you do all the first pass, the number in the last spot is guaranteed to be correct. Nothing else is, but the 5's got to be correct. So that's why I mentioned this. We're going to put it in a box. So that's just to indicate how much we've done. So this is guaranteed to be correct. Last element must be where it belongs. So after first pass. All right, now let's continue on with our method. So what we're going to do now in the second pass is exactly what we did for the previous pass. So we just do exactly what we did before. So we should compare these 2 and 3. Are they in order? Yes, right? So we don't switch. So that means 2, 3, 1, 4, 5. I'm going to just use blue so I don't have to keep switching to a red marker. All right. So we compared the first 2, they were correct. Now we're going to compare the second 2, 3 and the 1. Those are out of order, right? That means we got to switch them. So then we're going to have 2, 1, 3, 4, 5. And then we compare the last 2, 3 and the 4. Are those in order? They're in order, so we don't have to switch anything. And we're actually done now. We don't have to make a comparison between these 2. because we already know the 5 is in the correct place, so there's no point in comparing the 4 to 5. We already know that the 5 is bigger than the 4. It's got to be because 5 is correct. So we had to do 4 steps in the first pass, but we only have to do 3 steps in the second pass, and we're done. And at this point, we're guaranteed that the first 2 are now correct, or sorry, the last 2 are now correct. So we're going to start a third pass. Which is, we're going to start where we left off. So 2, 1, 3, 4, 5. We're guaranteed that the last 2 are in order. Last 2 in order now. I'll say correct. Last 2 done. I don't know. Done. After 2 passes. So the 4 and the 5 are correct. And let's continue on. So we're going to do exactly the same thing. So we're going to compare the first 2, the 2 and the 1. They're out of order, so we're going to switch them. So they're going to be 1, 2 after we switch them. And then we have 3, 4, 5. 4 and the 5 we're done with. So then we compare the next 2, the 2 and the 3. Those are in order, aren't they? Those are in order, so we don't have to do anything. So we have 1, 2. Oh, actually, we don't even need to write it, do we? I was just going to rewrite it. But that's it. So we just compared the first 2 and then 2 and 3, and we're done. We don't have to go any further because we already know that the 4 and the 5 are correct. So now we're going to start our fourth pass, which I will write here, actually. I'm not going to go to a new line. Fourth pass. So we've got 1, 2, 3, 4, 5. So we know the last 3 are correct after 3 passes. And all we got to do is we just have to compare these 2. And if they're out of order, we switch them. But they're in order, so we don't. And now we're done. Right? Because after the fourth pass, which we've just finished, we know that how did that happen? We know that this much is in order. But if you know all of them but 1 are in order and done, then the last one's done too, right? So 4 done after 4 passes. Which means the 1 is also correct because there's nothing to compare anymore. Okay? And so that is called bubble sort. And the reason it's called bubble sort is because in a pass, what's happening is, like in the first pass, it's hard to see because the 5 was already in the correct place. But no matter where the 5 was in the starting, like even if the 5 had started way up here, then what would have happened through the first pass is the 5 would have moved down to the second one, down to the third one, down to the fourth one, and then would have been switched. And that process where like the 5 or whatever moves to where it goes, that you would describe as like bubbling. If we were doing it in the other way, like if we were going from the end to the beginning, like instead of comparing the first 2, if we compared the last 2 and otherwise followed the same process, then what would be happening as you go across is that the number would be bubbling up to the top. In this case, it's like the 5 was bubbling down to the 5th spot, but that doesn't even sound like bubbling, right? Bubbles rise; they don't go to the bottom. but these bubbles sync. So the 5 sinks down to the bottom, and then the 4th sinks down to the bottom, although again it already was. And then the 3 should sink down to the bottom, but it was already there. So it's hard to see what was going on here because there wasn't very much bubbling in the bubble sort, but this method would work to sort any list of numbers. Okay, so the way I wrote it here is a pretty reasonable way to do it. I copied that method straight from the book. So if you're doing homework, or you're reading the note or reading the book, that should be exactly the book's method. Okay, let me put the algorithm here. Oops, I did that wrong. Oops, I did it wrong again. I did it wrong again. Algorithm 4, put it right there. Close U. Just going to close this right now. Lost it. And try this again. Okay. Here's what I'm going to do. I'm going to take this algorithm and put it where it goes. Did it magically get fast again? I guess it did. Okay, well, good. It means I don't have to restart Notability. All right, so here's the bubble sort. It's actually very simple code. Very simple code. So the bubble sort is much easier to code up than the binary search. And you do have to code up the bubble sort in the previous or in the next homework, I mean. So it's really simple. Let's just look at it. All you're going to be doing is, well, first of all, it says I goes from 1 to n minus 1. And remember how we do n for lists. So when you're doing the code, you're going to have to remember like n equals like the length of the a vector, like always. But after that, it's just a for loop, and then an if statement. So just a for, an if statement, and then an end to close the if, an end to close the for, an end to close the other for, and then an end to close the function. So this is a actually very short function to code up. And yeah, so it is what it is. So it's exactly the algorithm that we just did up here. And you will code it up. All right, so last thing in this lecture, we're at 58 minutes, but I don't want to have another lecture just for this insertion sort. So I'm going to say a couple things. So number one, bubble sort is easy to code. You can see that it is. It's just a few lines, but not very efficient. So you wouldn't want to use this in code that you were writing. Like if you're sorting a list of like 100 things, probably fine. If you're trying to sort like a list of like 1,000,000 things, then this is bad. And you probably think like, oh, well, when will I ever be sorting a list of a million things? Well, 1,000,000 things is just, 1 megabyte. If they're integers, like 1 megabyte of integers, or like 4 megabytes of, if you have like doubles or something, that's not a big data set, right? Like 4 megabytes is not that much. So, you don't want to be using inefficient sorting algorithms, if you think that the number of items that you're sorting might be big at some point. So this is easy to code, but is not great. The other one we're going to cover is called Insertion Sort. Is also pretty simple. And also not very efficient. So neither one of these is a great way to be sorting like big data sets, but they are what we have in this section. All right, let's talk about insertion sort. All right, so insertion sort is going to be, it's kind of what we did. It's kind of the same as bubble sort, but what I want you to know about bubble sort is when we're making comparisons, we're always comparing like um, elements 1 and 2, then 2 and 3, then 3 and 4, then 4 and 5, right? They're always right next to each other. You're always comparing one element with the next element, one element with the next, one element with the next, one with the next. And of course you see that in the code as well. Like when it says AJ and AJ plus 1, those are right next to each other in the list. So that's what you're comparing. So insertion sort is very similar to bubble sort, but the things that you're comparing are not right next to each other anymore. What insertion sort is like is if I'm going to draw on this and I'm going to get rid of it. Like insertion sort is like, instead of comparing the way that these highlighted comparisons are, they're like, well, what if you compared two that were right next to each other? And then you compared two, like the first one with the third one, and then the first one with the fourth one, and then the first one with the fifth one, right? Doing that kind of thing instead of comparing things that are right next to each other. And if you make your comparisons that way, but otherwise are doing pretty much the same thing as bubble sort, that is how you get insertion sort. Okay. So let's see. So just like before, I'll try to show you how this works with an example, and then I'll try to describe it a little better. So example. So let's sort the same list, 3, 2, 4, 1, 5. Three, 2, 4, 1, 5. We're gonna sort that. So let us see. All right, let me write it out. So we got I'm going to say first pass. They don't use that language, but so here's the idea. So we got 3, 2, 4, 1, 5. So we're starting out the same way we did with the bubble sort. So what we're going to do is we're going to compare the first two. So we're going to compare these two. And just like before, if they're out of order, then we're going to put them in order, right? Or sorry, if they're out of order, then you switch them. So we're going to switch them. Okay. So after you switch them, you've got a list that looks like this: 2, 3, 4, 1, 5. And what you know is that the 2 and the 3 are in the correct order. Okay. Now they're not done, but they're in the correct order. Right? Because we just swapped them because they were out of order. Right? So then what you're going to do is you're going to figure out where the 4 goes in that list. So I'm going to say second pass, but this is not really passes. Okay. Second pass. So I'm not doing anything. I'm just recopying it. 2, 3, 4, 1, 5. Okay, so what we did is, or what we're going to do now is we're going to compare the 4 with a 2 and a 3. So we're going to compare the 4. Let's see. So you're going to compare these two. Is that right? Hold on. Yeah, so it compares the 2 and the 4. And so the 4 is bigger than 2, so it leaves it alone. And then we just put those in order. And then what's going to happen is got 2, 3, 4, 1, 5. These are in order. And so after comparing the 2 and the 4, let me write that in blue. So you compare the 2 and the 4. 4 is bigger than 2, so you leave it alone. Then you're going to compare the 4 and the 3. And again, you don't have to swap them because 4 is bigger than 3. And so at this point, you got 2, 3, 4, 1, 5, and those are in order. Okay, so then for your third pass, I'm just, again, going to write the last one. This much is already in order, and we're going to be trying to put the 1 in the right place. So you're going to compare the 1 with the 2. And you compare the 1 with the 2, and because 1 is bigger than 2, what's going to happen is you don't switch them. I guess I probably shouldn't. Let me change this symbol here. You're not going to switch them. You insert the 2 where it goes. So like what we're going to be doing is you're not switching the 1 with the 2 because 1 is smaller. You're actually moving the 1 to be in front of the 2. And so what you get is 1 moved to the front, and then 2, 3, 4, 5, and this much is now correct. So as soon as you insert the number where it goes, then you're done with that pass. So then we're on our fourth pass. So we got 1, 2, 3, 4, 5, which is already sorted, but we don't know that yet. This much is correct, but unlike the bubble sort, when you're down to 1, you can't assume that the 1 left is in the correct spot. So you actually have to make the comparisons. So you have to compare the 5 with the 1. 5 is bigger, so you leave it alone. And then you compare the 5 with the 2. 5 is bigger, so that's not where it goes. Why am I... 1, 2, 3, 4, 5. Those are already in order. So then you compare the 5 with the 3. 5 is bigger than 3, so you leave it alone. Then you compare the 4 with the 5. 5 is bigger than 4, so you leave it alone. And so then you got 1, 2, 3, 4, 5, and we got to the end. And so now this much is done. Okay. And so the reason they call this insertion sort is because, like you saw happen with the 1 here, when you have to move something, you move it where it goes. And so you insert the 1 into the correct position. And the other one that we had to move was right here, is we insert the 2 into the correct position. And that's why it's called insertion sort. Now, something you can see here is, look at this fourth pass. the 5, like it was already 1, 2, 3, 4, 5. So this is actually done, right? This is already sorted. But we didn't know it was sorted. So we actually had to compare the 5 to the 1, the 5 to the 2, the 5 to the 3, and the 5 to the 4. And after we did all of those comparisons, then you know, oh, actually the 5 is in the correct spot. And so the whole thing is in order. And that's weird. Now, if you look at the previous step, the 1 was out of order, right? The 1 was actually supposed to go, should be first. And so when we make this first comparison, the 1 and the 2, we realize that 1 is actually smaller than 2. So 1 has to go all the way to the beginning. And then that's how it gets right here at the beginning. The point that I'm trying to make is this. This was one step because the 1 was really far from being in order, right? Like the 1 was way down here and it should have been way up here. And that actually made this a short third pass. Whereas the 5 is in the correct spot, and that actually made the fourth pass really long because it was already in the correct place. And so the point that I'm trying to make here is that the closer your list is to being sorted, the worse insertion sort is, right? It actually takes more steps. So if your list is close to sorted, then insertion sort is slow. Because it keeps making comparisons like this without actually moving anything. And bubble sort is kind of the opposite, I want to say. Whereas, like, for bubble sort, the thing that makes it you're either making a comparison and switching things, or you're making a comparison and not switching things, but the total number of steps is the same. And so what's slow is kind of switching things. And you only have to switch things when they're out of order. So even though both of these methods here, bubble sort and insertion sort, are not very efficient, they're not inefficient in the same way. Bubble sort is inefficient with things that are out of order, and insertion sort is inefficient with things that are in order. So if your list is close to being sorted, insertion sort is slow. If your list is close to completely out of order, or backwards maybe, then bubble sort is slow. So they're not opposites, right? They're two sorting methods that have stuff in common and some stuff that's different. But they're both, neither one of them is great. So I don't know. Let me get this algorithm on the page here. Have an idea. Oh no, it didn't actually slow down. Weird. Okay. And so this is the algorithm. There's nothing special about it. Yeah, I mean, there's nothing special about it. So this is what it is. It looks more complicated in here, but it does exactly what we did in the example. So you can think of it as this way. In the first pass, what's happening is you're trying to insert the 2 into the correct location, and you did right here. And in the second pass, you're trying to insert the 4 into the correct location. And when you're done when you're done. In the third pass, you're trying to insert the 1 into the correct position, and when it's there, you're done. And in the fourth pass, you're trying to put the 5 into the correct position, and when you finally do, it's done. So in the first pass here, you're looking at the second element, trying to get it in the right spot. So first pass, second element. Second pass, third element. Third pass, fourth element. Fourth pass, fifth element. So you're trying to put that one single element in the right place in each pass. And that's insertion sort. Okay. And this is the algorithm. I think I'm going to code this one up for you. So in the next lecture, I'm going to code this up in MATLAB, and I'm sure that we're going to talk about it in more detail when I do that. So I think that's going to be it for this lecture. Yeah, so good luck on your exam that you're working on, hopefully. And probably you'll look at this afterwards, huh? All right, so that's it for now. Talk to you guys later. Have fun with the exam.